In this video, we'll look at tf.functions. So let's go ahead and import the libraries first. Import TensorFlow as tf. And as we have seen in the previous video, we'll try to create a function in Python and then use the tf.function decorator. So tf, so here we have def and the function, let's say it's f, which takes in two input arguments x and y, and what it returns is the square of x plus square of y. And to this we are going to add the decorator tf.function, and so when the TensorFlow executes this, it will create a graph for this function. Now we can define the input values for x and y. So x is equal to tf.constant, and let's say we have the values 1 and 2, and similarly for y we'll create another variable here, and the values would be -1 and -2. Now when we call f with the input arguments x and y, what we get in the output is the tensor, which is shown over here, which is a rank 1 tensor. It has a shape of 2, and these are the values in the numpy array 2 and 8. Now we know that this is how the function is used in TensorFlow. Let's look at a variation where we are trying to append a value to a list using a function in Python, and let's see how TensorFlow works with this. So let's give this a heading called Append, and now here we'll create a function. We'll first initialize a list, so let's initialize an empty list, and let's call this list as xlist. Now we'll create a function, and this would be df, and let's call it f of x. And within this function now we'll create a for loop, which such as like this: for I in x, print I colon I, and then we are going to append. So xlist dot append I plus 1. So that's the function we have, and to work with TensorFlow, we are going to add the decorator at tf.function on top of this. So with this, then we can now create the input argument values. So x is equal to tf.constant, and these values could be an array, one dimensional. So it needs a square bracket, 1, 2, and 3. And now if we call f of x here, and then if we try to print the value for our x list, here we should see, so what we see here is we have the tensor in the output, which is this type, as we can see here. Now the difference here is that the x list is outside of this function, where we have the decorator and f of x and the for loop. What the document suggests is, instead of doing it like this, there is an alternative way to do this using t.write. So let's see how that would work. So we'll create a function, def function. This is again f of x, and here we'll create an tensor array. T is equal to tf.TensorArray, and we'll give it a data type. D type is equal to tf.int32, and let's give it a size of 0, and dynamic size is equal to true. So as new values get added, it will change the size of t automatically. And then we have the for loop here for I in range length of x, which is the input argument we have. And now to write to this tensor array that we initialized here, we would simply write t is equal to t dot write, and within this we specify I, which is the value that we are getting in the for loop, a comma x I plus 1. So at each of these index, we are going to add value of xi incremented by 1. And once that for loop is done, we can then return this value t dot stack. And now, and finally, we need to decorate this. So add tf.function. Now if we initialize value of x such that x is equal to tf dot constant, and here we specify values such as 1, 2, and 3. Now if we call f of x, we get this output where we have a tensor as output, and because everything here is in TensorFlow, this is the recommended way to perform append inside a function just using this dot write. Next, let's look at concrete functions again. We looked at this briefly in previous video. We'll look at one example again in this video. Concrete functions. And what concrete functions are the few characteristics about the concrete functions are they're built on fly, as the generic function is called. As the generic function is called. And again, it is called every time that either the type changes or the shape changes for the Python values, then a new concrete function is created. Python arguments. Now let's see examples of these. So we'll create a function again f of x, and we'll start by decorating it with the tf.function, and then call it tf space f of x, and then return the value of absolute value of x. Now with this, if we call this function, if we create f1 is equal to f dot get underscore concrete underscore function, so we get the concrete function for f. What this means is when when a TensorFlow runs this particular function, it will create a graph, and the get concrete function will get the concrete function that is within that graph. So we have done that for f1, and what we'll do next is we'll put a value here, just an integer value of 1 within this as an input argument, and then we'll create another function right here. This is f2. We have f dot get underscore concrete underscore function, and let's input a value of 2. Now if we print if f1 is equal to f2, if f1 is f2, is it the same concrete function? Then in the output we see that it's false, and that tells us that when TensorFlow created a graph while executing this function, when the input value was 1, it was a different graph, a different concrete function within the graph, and when the input value was 2, it was another concrete function in the graph. Now, what happens when using in these situations is this particular execution becomes slow because a new graph is created, a new concrete function is created within the graph. So to make this work faster, alternative is to input arguments that are TensorFlow arguments. So instead of input as of 1, we'll say input where tf.constant, and here we have this rank 0 tensor. So here we have tf.constant and we specify 2, and this is now faster because the only one concrete function is created, and that same concrete function is used in the second operation where we are trying to get the value for f2. Additionally, there are something called as input signatures, and let's look at an example of that. And again, input signatures are another way to tell TensorFlow that you can automatically convert some of the Python items into TensorFlow to make the code run faster, create less concrete functions. So let's create an function def f of x, and we'll return a value of x plus 1. And here we'll add the decorator tf.function. Now with this, we'll create input values of x. So let's first pass a vector, and let's create that by calling tf.constant, and we can have values such as 1.0 and 2.0. Next is equal to tf.constant, and we have two square brackets this time. Now if we try to get the concrete function f.get underscore concrete underscore function using the x vector, and then check if that is indeed the same concrete function as we would get with the x matrix. So f.get underscore concrete underscore function x underscore matrix, and here we see that that is not the case. These two input arguments create different concrete functions within the TensorFlow graph, and that's because we have two different functions or two different shapes right here. Let's look at another example where we can update a TensorFlow variable from within a function. And this is a recommendation from TensorFlow docs that the tf.Variable be defined outside of a function. So let's see how we can do that. tf.Variable is outside tf.Function. And for, let's say we define a variable var is equal to tf.Variable with a value of 1, and then we create the function add tf.Function and def f of x, and here we have var.assign add x. So we are adding the value from x to the tf.Variable, and by doing this we should be able to update the tf.Variable that outside this function. So now if we call f and we pass in an input argument tf.constant, let's say we pass in a value of 1, and now if we print var, here we see that the value is updated to 2, so we incremented the value of 1 by adding this 1 to 2. And this is a recommended way of working with a variable. Other way that is also possible is the regular using a return statement within the function. So let's say we define c is equal to tf.Constant and assign it value of 1, and then we create a function tf.Function, and here we define f, which takes in two our input arguments c and 1. So we have to pass in this as well as the incrementer that need to be added to c, and within the inside the function then we can perform the operation and then return the value of c. So here if we call this function f and we pass in the value c and then pass in the value of tf.Constant and value of 1 there. Now when we run this, we get again the output 2, but the difference is that here the TensorFlow variable is outside this function, and in the output what we get is a variable, whereas in this case the output that we get is a tensor. Now, couple of items to note as we move forward is tracing. So when TensorFlow is computing a graph for a function, the Python operations are executed only once. The Python operations are executed only once, and that's during the first time the code is run. And to test that, let's try this function tf.Function, and all these functions are directly from the docs. So if you need more information, you can always refer to the user guide. df, and here we can define f of a and b, and sorry about that. Now if we print, so printing at trace time, and here we print the value of a is equal to a, and then we print value of b is equal to b, and then we return value of b. So the first item, let's say we set the value of a is equal to 1 and we set the value of b is equal to tf.Constant, and let's say the value is again 1. Now if we call the function with the input arguments a and b, and when we look at the output, we see that during tracing in the first cycle, this was the print statement was executed. We have the value of a is equal to 1 assigned, and b is equal to this particular tensor, which is what we had passed here, tf.Constant 1, and we have the value of 1 right here in the output that is returned by b. Now if we change the input values a little bit, if we now say that we have the value of a is equal to 2, and if we have the value of b as the same as tf.Constant 1, and now if we run this time again, because we have this value that is different, it will create another graph, and therefore this line is printed again. And so we have a is equal to 2 in the output, and for b, the return value of b, we have 1 in the output. Now, however, if we now take this, copy this, let's say copy selection, and now instead of changing the integer value of a, if we change the value of b, and now if we run this, it uses the same graph as before. So the print statement is not executed. Python statement is ignored because the graph is already created, and the reason why it is using the same graph is because the value of a is the same and the value for the tensor is the same shape and it's the same type. So all we have done is changed one by 2. And so in the output, we get the value of b written as 2, as we can see here. Now let's look at a few ways in which TensorFlow has provisions where we can um, allow it to automatically decide what items could be converted to TensorFlow or data types. So let's create a heading here using type annotations, and this is to improve performance. The very first thing we'll try is we'll create a function def, and this is with hints, and these examples again are directly from the docs. So here we specify x is equal to tf.Tensor as an input. So that's could be the hint to TensorFlow that incoming value could be represented as a tensor. And here we can say tracing. I'm going to give this an arrow pointing left side, and then we'll return a value of x. And on top of this, so let's try one more thing. Here we can use the tf.Function decorator. This is the usual way we would write this, but now for allowing annotations, what we need to also input in tf.Function is experimental follow type hints is equal to true. So that's why we have the name of the function with hints, and we copy this, paste it here, and what we'll do, we'll also copy this line and we'll set it to false right here, and rest of it stays the same, and with we'll change the name of the function to no hints. Now with this setup, let's run this with hints and no hints and see if what difference it makes. The first item we'll try to run, we'll try to print f no hints, and we'll pass in a value of 1, and let me copy this and paste it here. Again, we'll create a new line, and similarly copy this and paste it here. We have value of 2, and again value of 2 here, and we'll copy this entire block, paste it down below, and here we'll use the function with instead of no, and here we have with, and what I'm going to do now is change all of these, and now if we run this, we should see the difference. So as we can see here, we have, when we run without hints, as we can see in the first two cases, we have the value of tensor tf.Tensor is 1, and we have the print statement executed. In the second case also we have the print statement executed, because we are not going to giving TensorFlow any hint that the values that are coming in could be represented as a tensor. But when we specify a hints is equal to true, in those cases, when we pass in a value of 1, the TensorFlow interprets it as a tensor and not just an integer. And so while tracing, while creating a graph, it does print the print statement very first time, but then second time it automatically detects these two as a tensor. It considers these two as a tensor, and therefore it doesn't bother creating a new graph. It uses the previous graph, and therefore the tracing print statement is ignored, and we just have this output right here. So that was it for this video. I hope in this video you got some additional information about how the tf.function works in TensorFlow. We'll continue with other topics in TensorFlow in following videos. Please like, share, and subscribe. I hope to see you all in the next video. Thank you.